There is a particular type of series known as a p-series. A p-series is of the form from n equals 1 to infinity of 1 over n to a constant power p. So that the terms of the series would be 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, and so on. A p-series will become very useful in the next lesson when we talk about a direct comparison test. P-series have the property that they converge if p is greater than 1, and they diverge if p is between 0 and 1, including 1. The proof of this can be done using the integral test. One over n to the p, a positive power p, is certainly a continuous decreasing function. Now, the reason that we stick to positive powers of p is because if p is negative, then 1 over n to the p would be able to be written as n to the p in the numerator, where p would then become positive. And this would clearly become a non-decreasing series. The terms would be non-decreasing and therefore would, by the divergence test, not diverge. So in order to make this have a chance at convergence, the terms of the series need to get smaller, and that requires the n to the p to remain in the denominator, and that can only happen if p remains positive. So with that in mind, we have a decreasing, continuous, positive function. So we can write this as the integral from 1 to infinity of 1 over x to the p dx. Using our standard technique of limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx, we have three situations that we should address here. First of all, we do have the idea that the series is supposed to converge if p is greater than 1. Second, that it is supposed to diverge if p is less than 1. And then it is also supposed to diverge if p is equal to 1. Now, the reason we're going to single out 1 as its own separate thing is because it will have its own separate antiderivative. So let's start for a moment with the situation where p is exactly 1. In that case, our integral, or our integrand, becomes 1 over x dx, which then has the very specific antiderivative of the natural log of x. This would become equal to the limit as b approaches infinity of the natural log of b minus the natural log of 1. Now, the natural log of 1 is 0. And the natural log of b will approach infinity as b approaches infinity. So this limit approaches infinity. By the integral test, the integral diverges, and thus the series diverges. So if p is equal to 1, the series will diverge. So that's our first situation. Now, the other two situations both fall into the same antiderivative. So let's start with this. Otherwise, the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dp, dx, can be rewritten as the limit as b goes to infinity of the integral from 1 to b of x to the negative p dx. And thus we can use the power rule. The power rule would have us add 1 to the power and divide by the new power. Now, regardless of whether we're talking about the fundamental theorem or the limit, in either case, p is a constant. And therefore, negative p plus 1 in the denominator is also a constant. That can be brought out in front of the entire thing. At this point, the fundamental theorem will yield our coefficient 1 over negative p plus 1 times the limit as b approaches infinity of b to the negative p plus 1 power minus 1 to the negative p plus 1 power. In which case, it doesn't really matter what p is, because 1 to any power would be 1. So what we have here then is really just needing to understand what happens with b to the negative p plus 1. And this is where we're going to have to break it down into either p is smaller than 1 or p is bigger than 1. If p is smaller than 1, but still positive, then negative p plus 1 will be greater than 0. Because the value of p is small in magnitude, like say 1/2 or 1/3 or 1/8, then it is made negative. So we have a small negative value plus 1. This will always result in a positive value because the 1 is bigger than the negative p. What this means then is that b to the negative p plus 1 is then b to a positive power. And regardless of what that positive power is, whether it's positive 1/2 or positive 2/3 or positive 8, as b goes to infinity, b to a positive power will also approach infinity. And thus, the limit of this whole thing is going to go to infinity. Thus, in this situation, the integral diverges, and thus the series diverges as well. The other scenario is if p is greater than 1. In that situation, negative p plus 1 would be negative, because we would have a larger value of p, such as p equals 3/2, or p equals 2, or p equals 5, then the negative p would be larger in magnitude than the positive 1, and would result in a negative value. So what we have then is that b to the negative p plus 1 would become b to a negative power, which would be 1 over b to a positive power. And we already know that b to a positive power is going to approach infinity, so this will approach 0. And thus we have 1 over negative p plus 1 times 0 minus 1, or negative 1 over negative p plus 1. Thus, the integral converges, and thus the series converges. Now again, the value to which the integral converges is not the same as the value to which the series converges. So while the integral may converge to negative 1 over negative p plus 1, the series converges to some other value. But the idea here is that for certain specific values of p, specifically when p is greater than 1, the p series will converge. For example, the series 1 over n squared, which is 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, etc. This converges based on the idea that it is a p-series where p is equal to 2, which is, of course, greater than 1. On the other hand, if we had 1 over the square root of n, also known as 1 over n to the 1/2, this would be 1 over the square root of 1, plus 1 over the square root of 2, plus 1 over the square root of 3, etc. This would diverge based on the fact that it is a p-series with p equals 1/2, and that is smaller than 1. There is one particular p-series that is interesting, and it is the value of p that is the border between converging and diverging, specifically p equals 1. Or simply 1 over n. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, etc. This series diverges. It is a p-series with p equal to 1. But as I mentioned, this is the border. If p was any bigger, the series would converge, and if p was any smaller, the series would diverge. This particular series is known as the harmonic series. It is actually known as the harmonic series because of its connection to music. In music, strings of the same material, diameter, and tension, whose lengths form a harmonic series, produce harmonic tones. So there is a mathematical connection between this particular series and strings on an instrument. It is a very commonly used series, again, as it provides the border between what is convergent and what is divergent. This concept will become very helpful in the next video where we talk about the direct comparison test.